Right now, the universe is mostly invisible to you. Not in a metaphorical sense, in a literal, physical, measurable sense. Every planet, every galaxy, every star that has ever burned across the night sky, every atom in your body, and in every body on Earth, all of it accounts for just 5% of everything that exists. The other 95%? Dark. That word is doing a lot of heavy lifting, because dark matter and dark energy are not the same thing. They don't behave the same way. They don't do the same jobs. And if either one of them vanished tonight, what happened to the universe next would look completely different, depending on which one you removed. Scientists have known about both for decades. Neither one has ever been directly detected. In the 1970s, Vera Rubin was measuring something that seemed boring: the rotational speeds of stars and spiral galaxies. Stars close to the galactic center should orbit fast. Stars at the outer edge should orbit slow. That's just gravity at distance. The same logic that makes Earth orbit the Sun slower than Mercury does. The outer stars weren't slowing down. They were moving at the same speed as the stars near the center, sometimes faster. By the numbers, that's not possible, unless there is far more mass in those galaxies than the visible stars account for. Something invisible. Something not producing light, not absorbing light, not reflecting light in any form, just sitting there, pulling. Rubin spent years trying to get the scientific community to take this seriously. Most of them didn't. She was right anyway. What she'd found was the clearest observational evidence of dark matter anyone had produced. Astronomers have since confirmed it through a technique called gravitational lensing. When a galaxy cluster bends and warps the light from a more distant object behind it, the degree of that distortion reveals how much mass is present, including mass no telescope can see. The amount is staggering. Dark matter holds the universe together. It's an invisible scaffolding that galaxies and clusters are built around. Without it, the stars at the outer edges of galaxies would spin off into empty space. You need something like 5 times as much dark matter as ordinary matter, just to explain why the universe is structured the way it is right now. Dark matter is strange, but it is at least a thing. Something with mass, something that gravitates, something that occupies space and shapes the matter around it. Dark energy is stranger. In 1998, 2 separate teams of astronomers were studying Type 1a supernovae, exploding stars that always detonate at roughly the same peak brightness, which makes them useful as cosmic distance markers. You know how bright the explosion should be. You measure how bright it actually looks from Earth. The gap between those two numbers tells you how far away it is. Both teams expected to find that the expansion of the universe had been slowing down. It's been 13.8 billion years since the Big Bang. Gravity should have been doing what gravity does, pulling everything slightly inward, decelerating the spread. The distant supernovae were dimmer than they should have been, not because something had absorbed the light, but because the universe had stretched more than the models could account for. Space itself had expanded faster than expected. Something was pushing, not from a point in space, from space itself, from every corner of the universe at the same time. Saul Perlmutter, Brian Schmidt, and Adam Riess independently arrived at the same conclusion. All 3 shared the Nobel Prize in Physics in 2011. What they'd found was a repulsive energy woven into the fabric of space, growing stronger as the universe expands, because more space means more of it. Think about what that means. More space creates more dark energy. More dark energy accelerates the expansion. Faster expansion creates more space. There is no break on this, no equilibrium, just outward, forever. Okay, right now you're probably watching this on a phone or a laptop, which means I'm going to ask you something technically unrelated to cosmology. Hit subscribe and share this video. I mean it in the most scientific way possible. The algorithm runs on invisible forces too. It's basically dark energy. Hit the button. Back to the universe. Dark matter holds things together. Dark energy pulls them apart. These two invisible forces aren't fighting each other exactly. They operate at different scales and time scales, but they are not on the same team. Fritz Zwicky proposed in 1933 that invisible mass must be holding galaxy clusters together. He called it dunkle materia, dark matter. Nobody paid much attention for about 40 years. That's not a footnote in science history. It's a pattern. Ideas about invisible things take a long time to stick, because invisible things are hard to trust, and because the person proposing them is often ignored first. Nobody knows what dark matter actually is. The leading candidates, weakly interacting massive particles, called WIMPs, and a much lighter hypothetical particle called the axion, have been searched for in dozens of dedicated underground experiments over several decades. So far, nothing. Which means either those particles don't exist, the detectors aren't sensitive enough yet, or the particles interact so weakly with ordinary matter that everything built so far has simply missed them. Nobody knows what dark energy is either. The simplest explanation on the table, that it is Einstein's cosmological constant, a fixed energy density built into empty space, fits the observations. But quantum theory predicts that value should be roughly 120 orders of magnitude larger than what we actually measure. That is not a rounding error. That is, without any exaggeration, the worst quantitative prediction in the history of physics. Something is either deeply wrong with quantum field theory, deeply wrong with general relativity, or deeply wrong with how the two are being combined. The names dark matter and dark energy were not assigned to discovered things. They were assigned to problems, two enormous gaps in the understanding of reality, labeled and filed, still waiting for an explanation that fits. Every observatory, every particle detector, every satellite ever pointed at the sky is trying in some way to answer what these things actually are. The universe you live in, the stars, the planets, the atoms in your hands, the light from the sun that woke you up this morning, is 5% of everything. The other 95% is still dark.